Hello, everyone, and welcome here today. My name is Diego Tononi, and I am here to talk to you along with my team. I'm here to talk to you about our automatic Injera maker. We're here to do a progress report. And before we get into the thick of it, I just wanted to talk to you a little bit about my team. We are four electrical engineering students at Arizona State University, and our names are Marina Capage, Joseph DeMassimo, Jordan Clark, and myself, Diego Tononi. So now I'm gonna pass it on to Jordan, and he is going to talk to you a little bit about the early stages of the fabrication and construction of our automatic injera maker. So there you go, Jordan. It's all yours. Thank you.
Uh, Thank you, Diego. And as mentioned, my name is Jordan Clark. I'm also a member of the Robotic Eats team working on the AIM project. I'll be going over the first attempt at building the prototype and what steps we took doing so. So the first thing we had to plan out was, the materials. Well, due to the low volumes and cost effectiveness of buying high volume, we decided to go with locally, commercially available materials that were of lower cost. The main component of which was the frame. So we used a perforated universal use steel framing members that are available at any hardware store. We did use aluminum for the parts of the frame that were a little bit weight conscious, so the rotating arm. We wanted to make sure that we weren't overbearing on our servo motors. Using those standard frames allowed us to use off-the-shelf standard hardware and fasteners to be able to mount our components as well as assemble the frame together. So the other big components mechanically for the prototype build were the servo motors and the batter dispensing manifold. So the servo motors had to be mounted to the frame in such a fashion to still allow for proper clearance of the rotating mechanisms. So we had to make sure that both could physically support the weight and test to make sure that the clearance was suitable. The batter dispensing manifold was actually built using a PVC pipe that was modified, pre-drilled, capped, basically fabricated to simulate a prefabricated manifold to dispense the batter. So obviously the main parts of the assembly were the electrical components, and we've added on. So last semester we only had our main components, which was the Arduino Duo controller, the servo motors, the pump, and the power supply. Well, we added a couple of components, one of which was the power supply was 12 volt DC, so we had to step that down to a 5 volt DC to run Arduino off of, but we had to have the 12 volts for the pump because it's a 12 volt DC pump. So once we added the converter, we added a power relay to be able to control the pump from the Arduino. Once we had all of our electrical components assembled and mounted to the unit, we wired it up, and then we initiated some preliminary programming on the controller, just some test programs to run to make sure that we could confirm that we had wired the unit up correctly, all the components were working, and we were able to test basic functionality like the rotation of the arms and dispensing unit. Well, thank you so much. Next will be Marina Copage, and she'll go over the next stage of the prototype build. Thank you.
Thanks, Jordan. My name is Marina Kopich, and I'll be talking about the automatic Injera maker's physical connections and operation. The AIM is controlled by an Arduino Duo board. As displayed in the image, digital ports 2, 3, and 4 are used to connect the green, red, and yellow push buttons respectively that are used as human-machine interface for the AIM. Digital ports 9 and 10 are used to control two 20-kilogram torque servo motors. Analog port 86 was used to connect the relay board that controls the pump, and the 5-volt and ground connections are connected to a breadboard. The breadboard power rails are connected to an external power supply, which is used to provide the 5-voltage feed and ground to the other components of the AIM, such as the servo motors and push buttons. As seen in the image, the push buttons are wired in a pull-down configuration using a 10 kilo ohm resistor to provide a high signal when the button is depressed. The Arduino Integrated Development Environment IDE cross-platform application was used to write a program to control AIM's movement. The code consists of three functions: setup, where it initializes variables and sets servo's initial position; the loop function, where it uses the conditional if statement to determine the state of the button and actions; and a kill switch function, where it will run only if an interrupt is triggered at any time. In a nutshell, the code for manipulating AIM performs the following. When the green push button reaches a high, the button is pressed. The AIM robotic arm enables a servo motor connected to the main frame and rotates 90 degrees counterclockwise and hold its position, while the second servo motor initiates a 2-sequence 180-degree rotation of the batter dispenser. Concurrently, the pump is activated to dispense the batter while the dispenser is rotating. Then when rotation reaches its original position, robotic arm rotates 90 degrees clockwise to its original position. The red push button is used as an interrupt, and that when depressed, it stops the operation of the AIM, and it stops the servo motors and the batter dispenser. Now I will pass it on to my teammate Diego Tononi, where he will present about regulations of the AIM. Thank you.
And I would like to take just a couple minutes to talk to you about regulations behind our automatic Injera maker. Because Team Robotic Aids is aware that for us to be able to sell our product on the US market, we have to meet certain standards or certain regulations set in place by the United States federal government. So after extensive research, we have found two agencies which are directly involved in setting and enabling and acting upon certain these standards. And these two agencies are the FCC and the FDA. Let me start with the the FDA first. Under Chapter 21 CFR 100.1c, the FDA sets in place certain requirements and certain rules for all those materials which are considered food grade materials. The FDA sets various parameters as far as the content of specific chemicals that can be present in these materials for them to be considered safe to be in direct contact with food. Uh, Team Robotic Eats primarily from a point of view, from a perspective of a time savings goal, we decided to go ahead and implement our design by using materials that are in contact with food, by using materials that were already considered food grade, so food safe by the FDA. So these materials have already been approved and they haven't been modified by Team Robotic Eats, and for that reason they maintain their FDA approval. Furthermore, we looked into some of the requirements that the FCC sets in place. Under Title 45, Chapter 1, Subchapter 5, Part 15, the FCC sets in place rules for for all those electronic devices that go in an appliance, particularly electronic devices that operate above a frequency of 9 megahertz. All devices that operate above this frequency have to go under analysis by the FCC for what are called involuntary radiations. Because anytime a device operates at above a certain frequency, there is a chance for it to involuntarily radiate electromagnetic energy, which in turn can couple into other devices and cause a malfunction. So for this not to happen, all these electronic devices have to be analyzed, and the amount of radiation that is allowed is set by the FCC for what is considered a safe amount of radiation, above which the device is not usable for household appliances. Luckily, the only electronic device that the automatic Injera maker uses is a Arduino Due. An Arduino Due is an electronic device. It's a logic electronic device that is created by a company called Arduino, which already has FCC approval. All their devices have been scrutinized by the FCC and have already been approved by the FCC for this type of application. So, given that Team Robotic Eats hasn't done any direct modification to this device, and given that the device has already been approved by the FCC, our automatic Injera maker is considered already up to FCC standards, and therefore it doesn't have to go through the whole process of getting approved by the FCC to be sold in the United States. So that was all I wanted to talk about as far as regulations are concerned. And now I'm going to pass it on to Joseph, and he's going to talk to you a little bit more about the few weeks that we have left and how we are going to complete our design and prepare for demo day. Thank you very much.
Thank you, Diego. I'm here to tell you how we are going to finalize AIM to pitch to our investors and for demo day. And that really comes down to 4 key traits. The flow rate testing, the frame rebuild, the fluid tube solution, and the component storage. The first key takeaway in finalizing is going to be the flow rate testing. In our original calculations, we had it to about 2 seconds of activation for our pump to spread the half a cup of batter, which is the standard for most Injera bread. And that's going to come down to the diameter of the nozzle holes inside of the pipeline manifold and getting that down with the spin time of the pipeline to ensure that the Injera batter makes it around evenly in that perfect swirl that we're hoping to see. That may take a little bit of altering of the code or the timing of the pumps with the pressure, and that'll be a constant cycle of test versus application to find out the right perfect amount. Next, we have the flame rebuild. Initially, it was a prototype build made out of angle iron. There's going to be 2 theories of thought here. We're either going to go with the hard plastic, which will make it more cost effective in the end, but might not be able to supply the full brunt of the weight of the pipeline manifold in its spin. If it doesn't, then we have already taken options to go to a thin metal with brass fittings, raise the cost slightly, but it will provide that support that we really need. And also we're going to add adjustable pieces so you can adjust the height of the pipeline manifold and the legs in case you have a wider base for your hot plate. And then we're going to add a little rubber pieces on the end just to add that little bit of tabletop traction that'll really help in the kitchen. Next is the fluid tube solution, and that's because right now we're currently using a stiffer tube from the pump to the pipeline, and if that is too stiff and provides too much tension on the final product, we're prepared to go to a smaller diameter tube, which will get rid of that tension and make it more lightweight and flexible. We do have a few options there. And then for the fittings to release tension, we're thinking about either an L bracket coming off the pipeline manifold, which will just eliminate the use of the tube in itself, or a gyroscopic option, but we don't want to raise the cost too much. So we shouldn't have to go that route, but we are prepared if we need to. Last but not least, our product does spray liquid, so we've got to make sure that all of those electronic components are secure inside of a waterproof box. That's being handled just through a plastic electrical box that'll contain everything from the Arduino to the power supply. We're going to mount that towards the bottom of AIM on the back side to kind of counterweight the arm, as well as mounting the pump to the frame itself a little bit below the arm to where you can still adjust it on the height of the frame. In conclusion, we're on pace to finish AIM in about the first week of April. That'll give us plenty of time to finish the demonstration materials. That'll include the 3D model diagrams and our pipeline manifold catalog in case you have an odd-shaped hot plate and you need to order a specific modular version of it, you can do that. This learning has been amazing for Robotic Eats, and we are just ready to take this to the next step. And we really think we have a product that we could sell and market to restaurants around the country. Thank you.